Today, we will be focusing on our newest package, DFM 5x6 Dual Side Cooling, and how this package can improve the thermal performance of your application compared to a regular DFM 5x6. Some of the information we are going to be discussing along the presentation is a detailed comparison of dual side cooling and a traditional MOSFET technology like the normal DFM 5x6. Heat transfer capabilities and thermal performance of each type, advantages of 5x6 dual side cooling MOSFET, and discuss how we can solve real-world design challenges. First of all, we are going to talk about MOSFETs in general, what MCC can support at the moment. This is a summary of the products that MCC can support. We have divided them into small signal and power MOSFETs. And as you can see right here, you can find the most important parameters that you look at the beginning when you are looking for an alternative or some device that you will require or you will need for your application. For small signal MOSFETs, we have different type of packages. The ones that you can see right here listed, SOTs 23, 323, 363. You can see all of them right here. We also have ACQ certified products with different configurations as well. N, P, dual N, dual P, or combined. As an additional feature, we also have products with additional ESD protection. Something to add here is that we only have enhancement mode MOSFETs. And as I just previously mentioned, we can improve our HBM by promoting products with additional ESD protection from gate to source, up to 2 kVs. For power MOSFETs, we have up to 900 volts. We also have products in the sub-milliohms range and up to 320 amps considering case temperature. The packages that MCC is focusing the most are leadless packages like the Deep FN 2020, 3333, 5x6, or the Tall 8 package. Right here you can find several applications where power MOSFETs can be used. For low signal or low power applications like high-speed line drivers, open collector or push-pull digital interfaces, up to switching mode power supplies, or half or full bridge for motor controls, synchronous DC to DC converters, or for linear current controllers as well. For O-ring or hot swap inrush current applications for low or high side drivers. The technologies MCC is focusing right here, we are showing MCC MOSFET technology. For medium and low voltages, MCC is focusing on trench and split gate trench technology. You can identify if a part number is split gate trench just by checking the part number. There will be a letter Y at the end of it. And if you require ACQ products, they will have HE3 or will have Q. We have these two types of ACQ products available for your applications. For high voltage applications, we have super junction technology. MCC also has several planar MOSFET technologies, but at the moment, super junction is the technology MCC is investing. Here you can find our package roadmap. This is a general overview of the packages and technologies we are implementing on those packages. Something really interesting here is that we are to implement wire bonding, ribbon bonding, and copper clip on different types of packages like DFM 3333 that will use also ribbon, or the LF pack 5x6 that we are also working and developed and released in the upcoming months. Today, we're going to talk about the DFM 5x6 dual side cooling with copper clip technology included. Right now, we have just released 2 good products with ACQ certification. We will also release industrial grade for industrial applications or power tool applications. Now, we're gonna move forward on regards to DFM 5x6 dual side cooling with copper clip technology included. For these products, we are using split gate trench MOSFETs that are allowing us to have better and lower RDSon and much lower gate to drain parasitic capacitance. So at the end, it will help us with EMI, but also reducing conduction losses, while we maintain a decent input capacitance as well. It is a ROS compliant product with also a really low thermal resistance for bottom and top. Here you can find some of the most common applications where this power MOSFET can be used. And something to add here is we are showing the cross section of the device. So at the top, you will find a clip technology in this case, where you will have the exposed pad at the top and it will be connected to the source pin. The chip or the die will be here and it will be soldered to both clips at the top and at the bottom. So what we are showing here is the internal structure of this device and how it is connected internally. In this case, the lead frame at the bottom will also have an exposed pad in this case and will be connected to the drain pin. I would like to add something here about copper clip technology. We are showing here the differences between using copper clip and using wire or ribbon bonding. In this case, we are taking two MCC part numbers. The first at the left is the dual side cooling, and the one on the right, the mccsemi 180, is wire bonding DFM 5x6 device. So in this case, you can find how the RDSon can be reduced by almost 100% and how the junction, the thermal resistance junction to case can be also reduced by something similar. So in general speaking, the resistance can be reduced by at least 95%. The package inductance can be also reduced by at least 90%, and the thermal resistance can be improved by at least 28%, right? So the major differences will be, as you may see right here, because of the aluminum ribbon and the top die attach. It will help us to increase the current capability of the device within the same area. So it means you will have higher power densities within the same area, but also it will help you with the switching performance since you are also reducing the inductance of the package. So it means you can have a better EMI performance and lower power losses as well. So all these technologies are implemented in our newest DFM 5x6 dual side cooling. The exposed pad at the top, the split gate trench technology, and the copper clip technology as well. So all of them combined will give us a really attractive and interesting product that can be used in several applications. In this case, we are showing a comparison between one of the newest MCC products and some other two suppliers that are right now in the market. As you can see, we have really good and similar electrical characteristics. Our RDSon is a little bit higher. This is something that we will be improving in our next generations. But as you can see, we can handle just as much current as these other two guys can, and this is because of our better thermal performance in general compared to these other two competitors. This is only a datasheet comparison. So what we have done here is performing several tests on MCC and the other two suppliers just to show how we perform and the improvements that can be seen from these measurements. On the top left, we have the transient thermal graph, single pulse from junction to case top. Our device is in red, and as you can see in the transient behavior, we have some room of improvement for next generations. This is something that the team is checking now, but in steady state, you can see how our product has much lower thermal resistance than the other two guys. In case of the junction to case thermal resistance bottom, on the right bottom, you can see how it is behaving just like the other two guys in the transient area right here on the left, but how the thermal resistance in steady state is much lower than the other two guys, and it is helping us to reach these high currents compared to supplier 1 and supplier 2. In this case, we're just showing the differences on steady state compared to all these other two suppliers, and showing a 31% improvement compared to supplier 1 and almost 9% compared to supplier 2 on steady state junction to case top, and something similar from junction to case bottom, 47 and 52% of improvement comparing our device, in this case the mccsemi 330N04Y compared to supplier 1 and 2. One of the major applications where dual side cooling in the automotive industry is in electric power steering. They have two motors that needs to be controlled, triphasic motors. And in this case, they're showing 6 power MOSFETs for doing that. And all of them are dual side cooling. So in this case, our products can be used in this type of applications due to the really attractive electrical and thermal performance. These are the two products we have just released, and they are ready in our website. So all the information can be found there. And if you require any additional information, please contact your local MCC support team, and we will be more than happy to help you. Moving forward, we're going to be talking about several topics here: heat transfer, thermal pad, thermal resistance, and thermal models. So we are going to be showing here some of the theory or information that it is required in order to show you how our DFM 5x6 dual side cooling behaves. First of all, we're going to be talking about heat transfer mechanism. So in this case, heat is the amount of energy that it is transferred from one system to another, or it could be also between system and the environment. And this is a result of temperature differences. There are three major heat transfer mechanisms. One is thermal conduction, and this is due to the movement of the molecules of solids. In this case, what we are showing here is that the thermal resistance, heat is always going from the surface or the point with the highest temperature to the surface or the point with the lowest temperature, but always using the pad with the lowest thermal resistance. So this thermal resistance is really important and needs to be reviewed and checked. So there are three major heat transfer mechanisms: conduction, convection, and radiation. And all of them depends on the physics. So in this case, conduction is due to the movement of molecules of solids, and they will have certain heat path that needs to follow, in this case, the thermal resistance. In this case, in order to reduce the thermal resistance, what you have conduction is by increasing the contact area or reducing the distance between the two surfaces or the 2 points or the two areas or volumes, but also by increasing the conductivity constant. So for thermal, it's the conduction. For thermal convection, heat is transferred by flow of liquids. In this case, it could be air, it could be water. And in order to reduce the thermal resistance, you will need to increase the area or increase the liquid flow in this case. For thermal radiation, the thermal resistance can be improved or reduced by increasing the area, the contact area, or increasing the emissivity constant in this case. For radiation, electromagnetic wave is emitted from the surface of an object with certain temperature, with certain wavelength that corresponds to that surface temperature. So it is transferred through space or vacuum and does not need a medium for that. So all these three heat transfer mechanisms are present while you are working with power elements. And it is really important to understand this because we will be able to understand how heat is transferred once it is generated inside of the junction. So right here, it is a heat generator. So it is dissipating power. So power will produce heat, and all that heat needs to get away from the die. So inside of the product, inside of the power element, it will spread out via conduction. Right? So once it reaches the PCB, all that heat was also spread out via conduction until there is nothing else where the heat can go. So it will start spreading out via convection and radiation. In this case, you will find how the heat which is generated in the die will move, right? The thermal path that it will try to follow. So from the die, it will go to the die attach, the lead frame, the package, and the PCB. So all of them are gonna be under conduction, and radiation will be from the PCB or the package through the air. So right here, we are trying to summarize all these resistances. From junction to case will be the thermal resistance top, and from junction to bottom will be the thermal resistance bottom. In blue, you will find the other two resistances, convection and radiation through the air. And in green, you will find the thermal resistance that the PCB will add once the device is attached to it. It's really important to understand that the temperature could damage your power device. So it is really important to make sure that the junction temperature never surpass the maximum junction temperature listed in the datasheet. It could be 150 Celsius degrees, or it could be 175 Celsius degrees, depending on the part. So sometimes it's quite easy to calculate that junction temperature, but some other times it's really complicated, tedious, and really time consuming by doing those calculations by hand. So it's much easier if you can simulate them by using a thermal circuit, and it's quite easy by doing it by implementing or using Foster models, right? So in this case, it's quite really simple. We have just fitted this curve by using nonlinear numerical methods, in this case Gauss-Newton, and we are trying to fit this curve by using this expression right here. This is a sum of several exponential terms, and we are only getting these elements right here, the thermal resistances and thermal capacitances as well. So it's quite really simple. The only thing about using Foster models is that the internal elements that will be in the model do not really have any physical meaning. So it's just a matter of a black box where you are going to be having the junction temperature, and that's it. There are some other models that MCC can also offer, in this case Cower model. It will have like a different distribution, but it is based on the Foster model. It's just a matter of using it in Laplace form and putting in this form right here. It's quite really simple, but it's easier to add some additional external networks like the PCB, like heat sinks, or thermal interface materials as well. So MCC can provide both thermal models for your reference, and you can use them for simulation as well. We have here some information about the thermal interface materials. So this is a thermal compound that it is used between the two surfaces, in this case the power element and a heatsink, for example, or a metal enclosure that will be attached to it. It's just to make sure there is a fully engagement from a thermal perspective between these two elements. There are several products that can be used: graphite pads, thermal grease, gap fillers, tapes, phase change materials. All of them will depend on the volumes, on the price you're looking, but also on the thermal conductivity constant. Right here, there is an example of one of these thermal interface materials. If you see it, This is not like a thermal resistance, this is a constant. So you need to calculate the thermal resistance of this thermal interface material, and it's quite really easy. It is just the ratio of the thickness over the area. So, and it's quite really easy to follow this equation right here. For this example, we are considering a thermal conductivity constant of 0.79 watts per meter Kelvin, and we are considering that we will use it in our 5x6 dual side cooling MOSFET, that the thickness will be approximately 0.04 millimeters. So by doing these calculations, we will end up with this thermal resistance 1.68 Celsius degrees per watt. So this value, we will use it later for our simulations. Finally, we will show the simulations and test results. So right here in this table, we are showing two MCC part numbers. Both of them are DFM 5x6 copper clip, and the only difference is that this guy over here on the right is our dual side cooling. So this is the one with the exposed pad. So in this case, we're using the body diode of the power MOSFET. So in this case, we're showing the junction temperature rise under certain test conditions. So we are applying 15 amps during 3 hours with an ambient temperature of 20.5 Celsius degrees. So in this case, we're using an FR4 1 ounce single side copper PCB. And the heatsink will have these dimensions, 15 millimeters by 15 millimeters by 14 millimeters, and it is made of aluminum. So here we are using the body diode in order to run these tests. So as I just mentioned, we are applying 15 amps, and this is the voltage drop we are having on the body diode. So once we measure this voltage, we can determine how much power the package is dissipating. And since this guy, obviously they will have some differences. The regular DFM 5x6 will have a little bit less power dissipation due to the voltage drop of the body diode, and we will have a slightly higher power dissipation on the dual side cooling because the body diode will have a slightly higher voltage drop. So once we have this power dissipation, we are estimating this junction temperature, right? So we are measuring the case temperature, and then using the junction to case thermal resistance, we can estimate the junction temperature. So you can see right here, the DFM 5x6 dual side cooling is dissipating higher power. The junction temperature is much lower, and this is because of the exposed thermal pad. Both devices are using the heatsink, but because of having the exposed pad, you can have a much better performance. So it means you can carry more current or use this device in a more problematic ambient temperature, if we can say it in that way. Something that we need to calculate in order to simulate this circuit is the heat capacitance. In this case, it was not mentioned in the datasheet of the heatsink, so we need to calculate it. And it's quite really simple. It's just a matter of multiplying the specific heat capacity, the density, and the volume of the aluminum. So all these three parameters can be found and calculated. So at the end, just by multiplying all these values, you can end up with the heatsink thermal capacitance, which is gonna be about 84.7 joules per Kelvin. So this is the model we're gonna be using in order to simulate the thermal performance or the thermal behavior of this heatsink. So right here, you can find the simulation results, and this is in steady state. Obviously, you will see the transient behavior, but we are gonna be comparing these results with the ones that we measured. In this case, in green, we are showing the Cower model of the regular DFM 5x6. And here at the bottom, in brown, you can find the Cower model of the dual side cooling DFM 5x6. And as you can see, we have separate models, but they are connected right here. These two nodes are connected, thermally connected. This portion on the top will be the top Cower model, and in the bottom will be the the bottom power model. Something really interesting about this is that you can add, in this case, a voltage source that will be the temperature, but you can have different temperatures in this case because all the surrounding elements can add more temperature. So in this case, we are adding like 2 more Celsius degrees to this, and the ambient temperature that could be 25 Celsius degrees, for example. We are applying a current source right here, 7.66 watts for the regular DFM product and 8.13 watts for the dual side cooling. And we have also added the TIM thermal interface material, thermal resistance, and we have also added the capacitance, the heat capacitance of the heatsink, but also the heatsink thermal resistance as well. So it's quite really simple to click run and get these results. In this case, we have run this simulation for about 3 hours, the same time that we run the tests. So in this case, you can find right here in the steady state portion how the junction temperature matches really well to what we have tested in real life. 166 versus 165 and 142 versus 143. So what we are showing here is our capability of providing thermal models for your reference. So you can just change the power pools that will be injected and you will get the transient and the steady state performance of our product and of our power elements without the necessity of making prototypes and measure them and wait 3 hours to get the results. It's quite really simple, and MCC can also provide those models for you. Something else that we are showing here is how the dual side cooling product can be really interesting on certain applications where really high powers are required within a really small area. So you are looking for power improvement or increase the power density, right? So dual side cooling package could be also really interesting for certain applications that we have just mentioned and we have just shared. So that's all. Thanks for watching. Please reach out to us for any kind of commercial or technical support.